Good afternoon. Okay, can we start now? All right, so it's my great pleasure to introduce foundation lecturer this afternoon, Kerrie Mengersen from QUT, a woman I've known for a few years now. And she's going to speak about the new Bayesian statistics for the 21st century, if I'm not confusing the titles. I mean, she has been contributing a lot to Bayesian statistics all over these years and continue to do so. So I'm very looking forward, and we are all very looking forward to her vision of the field. Kerrie.
Thank you. Well, hi, everybody. Thank you all for coming, and thank you very much to the ISBA organisers for the invitation to speak here. It's a bit daunting to speak in front of people who know a lot. What? Oh, okay, all right, I'll use this. All right. It's a bit daunting to speak to people in the room who know a lot about everything. I think if we picked any topic to talk about, then there obviously would be experts in the room here. So being Bayesian in the 21st century, that's all of us. You know, we're all in the middle of this Bayesian world now. And so I thought about what can I speak about that would be potentially of interest. And so I thought I'd tell you a little bit about what I do in my sort of day-to-day Bayesian life. Our Bayesian story, if you like, once upon a time, long, long ago, it didn't seem that long ago actually, but Bayes and obviously, you know, the world started for us with Thomas Bayes and Price, and they were figuring out about this new Bayesian ideas. And the two real sticking points at that time were about the question of priors and the question of computation. So how do you set a prior for a Bayesian analysis or Bayesian methodology, and then also how do you do the computation? And the solid line here is really there was a great interest in Bayesian, at the beginning Bayesian ideas, but then they sort of fell away with these two big debates about priors and computation. Meanwhile then, there were some people who really picked up the pace in understanding about priors, and then certainly about computation. The dotted line is where the frequentist approaches, sort of instigated by Fisher and others, really started to take the fore as these debates and sticking points around priors and computation came about. And so the dotted line sort of started to take precedence, or the rise. And as I said, you know, there was Jeffries who did a lot of work in the foundations of priors. And then Gieman and Gieman really sort of opened our eyes to how we might do computation through MCMC. Then there was the work of sort of putting all of this together through people like Gelfand and Smith, who really sort of set the scene for us to be able to do Bayesian analysis. And obviously there's a whole raft of people in the middle here, and this is just my little potted history. And you can see then the solid line sort of starting to take a rise and really rising exponentially and continuing to rise. And so this is where we are now in our story. This is our story here. And when I talk about my story, which is sort of like mystery, I was going history, mystery, you know, what do we get? So this is a mystery because it started out not as in the Bayesian world. I started out doing a PhD, like many of us here, especially older people, who was in frequentist world. And some of the missionaries to Australia in the early days for Bayesian statistics, there wasn't a lot of Bayesian statistics in Australia. And we had visitors like Julian Bisag and Peter Green who who came and spread the word and showed us about Bayesian statistics. And then as I started to learn about Bayesian statistics from some comments that Julian Bisag made about the work I was doing at the time at a conference, and also a person I was working with then was Richard Tweedy, who was a probabilist and a very good statistician. And one day Richard came to me, I was working on ranking and selection, and Julian Bisag said, you know, you can do this so much more easily in a Bayesian framework, and here's how you do ranking and selection with MCMC. Of course, it's very straightforward, and here's what happens with spatial modelling, and he was doing a lot of the early work in spatial models, and really sort of showed me about that sort of modelling framework. Richard Tweedy came along at the same time, and he said, you know, there's this new thing from a probabilist perspective, Markov chain perspective, he said, a new thing called MCMC, and I think it's magic. And so it was really inspiring and exciting time, because you had these people doing new modelling. You also had these probabilists and coming in who were so excited about, you know, an application for their Markov chains and their probability and all this sort of stuff, which was all really new. And there was a whole lot of energy in this space as well. I then accidentally met a whole bunch of people at the very first conference I went to overseas, which was at Purdue. And so I was so excited about going overseas from Australia, you know, my big overseas trip, and I ended up in Purdue, and I got out of the plane and went, where am I? You know, and I was at a ranking and selection conference, and there were these people there, Jim Berger and Christian Robert, and you can see some of the others there as well, Ed George and Robert Walpert, who were this group of Bayesians, and that really sort of changed the course of history. And so the rest really is the story on why I'm doing what I'm doing. So, you know, I'm grateful to them in most ways. I'm very grateful to them, and they've really been wonderful inspirations to me. The other inspirations, of course, were people in Australia who started to I started to learn about people like Robert Conn, people who also came to visit Australia at the time, who were really instrumental as well, and who also gave me a lot of mentoring and advice. And then more recently, then my collaborations with people like Judith and Antonietta have been really inspiring as well, and kudos to them for any of the work that I do. And now there's people around the world that I know, my family, in Bayesian statistics, and I consider myself very lucky to be in this community and to know many of the people here and to be able to talk to you today. The little green wobbly line there is really the emergence of machine learning and those sorts of techniques as well. And I think what I'm trying to get to is this sort of merger of machine learning and statistics, which is really setting a scene for the 21st century and the work that we do. So in the early days then, what we saw was like statistics, probability, computing, and the applications all coming together in this idea of early Bayes. But then what we've seen really, so from the early days then, this was the first Bayesian statistics conference at Valencia. So I just put up here the people who were giving invited talks and discussions at that meeting, and many of you may know those names that were there. So these are not just names on papers, these are real people, and just amazing foundation members. And this was the first proceedings of the Valencia conference. And what I did was to take a snapshot or a word cloud of the topics that were covered in that first meeting. And you can see here a lot of the topics here are topics that we are still grappling with now. So even though we've come a long way, we're still challenged by many of the topics that were challenging people back then. I then looked at, now we've come through modern Bayes, so from the early Bayes to the modern Bayes, and what are the sorts of things that I think are really sort of challenging now to us? And we still have that really strong importance of theory, methods, prior inferences and algorithms, But now we're spreading that out to combining with machine learning, computer science, data science. We've also got lots more data, different diverse data, deep kinds of models where we're really able to now grapple with the true underlying mechanisms in a problem, and new kinds of algorithms and computation. We are looking now not only solving those kinds of problems, but really starting to get to those software platforms, the products, the packages, software packages, and also the platforms, and embedding our work into organisations. So we're seeing a lot of Bayesian methods that are now bread and butter in different organisations. And we're seeing these really complex challenges that we're now able to address through Bayesian statistics. And finally, the question of AI and how we engage with AI, but also of ethics as well, data sovereignty, data governance, privacy, and so on. And I'll point out to Christian again here for the work that's happening in the area of privacy as well. And so I then looked at, just the same as the word cloud for the first Bayesian conference, I looked at a word cloud for ISBA here. But I must admit that I was translating this from ISBA, the ISBA program, and I got to day 1, and this is what it looked like. And I thought, you know, it sort of tells the story enough without me going through days 2, 3, and 4, and 5. But you can see here the depth of the work that we are doing. This is one day of our conference, and this is what we are doing. So, you know, kudos to everybody here for this amazing amount of knowledge that we are generating and sharing at this meeting. So we've touched on a few topics that we collectively thought, my colleagues and I thought were important in being Bayesian in the 2020s. And this is a review paper in the Philosophical Transactions of the Royal Society. And the topics that were covered there were these. So you'll see some of these, you know, intelligent data collection. We can collect data, but how do we do that in an intelligent manner? We don't need all the data. So how do we make sense of and good decisions about what kind of data to collect? New data sources, complex models, transferring models from one place to another, purposeful software products, as I've described, federated analysis, which I'll touch on a little later, and very much personalisation. We don't need the model that's going to suit everybody. I want a model that suits me. You want a model that suits you. So the mystery challenges for me, my story and my challenges, I'd like to talk about how I'm really trying to, and sort of moved more into this area, develop some platforms and products that are really trying to move the needle, if you like. It sounds really, you know, silly, I guess, in this context, because there's many people in this room who are doing the same thing. We're really trying to find ways to grow products and platforms based on Bayesian analysis that are going to sort of make a difference, if you like, or address a particular challenge. And in doing so then, in looking at those applied challenges, the sort of space that I stand in is looking at an applied challenge and then finding the methodological innovations or the questions that come out of that and how can we address those. And most of us do that in the room, you know, but to different extents. And so some of us are more on the applied side and then find the methodological or the compute problems. Some of us are more on the method side and find the applied problems as well. And so, you know, I see that there's this nice intersection where where many of us play. So I'm going to see if I can get through 4 examples. When Christian stops me mid-sentence, then we'll see how far we get. But I'd like to look at these different products or platforms that we're trying to build, and then just touch briefly on some of the sort of the questions that have arisen from those and how we've been looking to address them. And so the first one is Virtual Reef Diver. And so I do a lot of work in environmental and conservation areas, and one of the areas that I've worked in for a long time is looking at conservation and management of our Great Barrier Reef. Now, the Great Barrier Reef is 2,300 kilometres long. It's like past Italy, So it's a long reef. You can see it from space, and we've got a number of different monitoring sites, great monitoring data over 20 years for the health of that reef on coral, but there's a lot of space in between that is not being monitored. Now, the work on actually monitoring these long-term monitoring data that we have and analysing those has really, there's been a wealth of work in that area. And some of that has been done by people in our team, and I just point out Julie Versaloni is really leading some of this work. And this is trying to understand like the fine-scale changes in the reef and the coral composition and what's actually happening for the coral on the reef. I'll also just shout out to Katie Buckhorn, who's just finished her PhD. She's been looking at a lot about adaptive design, and so if there's people in the audience who are interested in adaptive design, Bayesian approaches for this, and especially in the area of anomaly detection, and so not only for the reef but also for waterways generally, and trying to do that, and also with work with Edgar Santos Fernandez there, who's trying to do a lot of like large-scale monitoring quickly. So I'll point to those papers. With our virtual reef diver, this is a platform that if I go back to this one here, what we've done is we've said, well, there's a lot of areas on the reef that aren't actually being monitored. How do we monitor those? How do we learn about the gaps? Well, there's any number of divers out there with their cameras, right? And so what we can do is we can set up, what about if we set up a website and we allowed people to upload their photos to the website to geotag them to the reef. And behind the scenes, we extract information from those images and we can include it with our data. And the question is, how do we extract from those images? Well, we could use machine learning, and there's some work that we're doing in that, or we can use citizen science. So we can use people from around the world who can go into those images and annotate them for coral, reef and sand. We can then extract that information and we can use it in our models. And so this is a platform that we have developed for this purpose. And as you see here, then it's got a lot of attention, a lot of activity. Won a Eureka, was a finalist in a Eureka Prize in Australia for this platform. So it's more than just a website. We do take these images that people can provide. We then annotate them. You see in the middle image at the top there's little circles. We ask people from anywhere around the world to go in, identify areas as coral reef, coral sand, or algae, etc. That gets written to a back-end database. We then use that in our models, our statistical models, which then provide more estimates of the health of the reef and spatial maps. The value of citizen science in this case is demonstrated in this figure here. Using this information, on the right-hand side is what we get when we try to model with just our long-term monitoring data across the site. The left-hand picture is what we get if we use all of the data, including our citizen science. So it's well worthwhile thinking, there's miles of citizen science projects out there now. But there are challenges in using this. One of the challenges is, how can we trust the citizen science data? Right? And the second one is, how can we transfer a model that I know a lot about now on the Great Barrier Reef to an area where I don't know very much about, like the other reefs of the world? And so Edgar Santos Fernandez here, this is his picture from Google Scholar. He looks somewhat like this. He has been doing a lot of work in like finding out how we can regularise or increase our trust in citizen science data. This is a paper in ISR that's just appearing. And, one of the ways that we've been looking at this, just to show you, is through a 3+ model, which is an extension of the RASH model. So you have the expertise of the citizen, you also have the difficulty of the image, and then you're going to include those in the actual model and the prediction. And so if you look at this kind of model, then we have for user I, image J and point K, we're going to have ask if the point contains the target class, yes or no, and then from this it becomes the regular sort of RASH model, where we have a latent ability of the user, a difficulty of the image, discrimination parameter and a pseudo-guessing parameter. But here we also include a spatial component. So the images then are going to be next to each other, and so there's this kind of, the difficulty of the image is going to borrow from the information around the surrounding images. And so this spatial inclusion here is very useful here. When we did this then, we were looking at some examples. We set up a crowdsourcing example through using Mechanical Turk. You can see some of the information there. We also looked at through a simulation study as well, and we could show that this method works, and we actually get much better predictions by correcting for a person's expertise and the difficulty of the images. The interesting thing is through this too, we identify who our experts are in our citizen science area, and that's really helpful for us because we can either tailor methods, education methods for those who are less expert, and we can also just focus on the results from the annotations from our experts as well. So we're working a lot on that. We pushed that harder then to looking at larger data sets, and so this was over 1 million images in many locations, and we get posterior estimates for, in this case, this was for different species, and we can also see where those species are, so which species are harder to identify than other species. So basically this kind of measurement error model, or this is really useful for us for combining and adjusting crowdsourced geospatial data. These models outperform current approaches. There's a lot of other methods that have been developed from this as well, but they really do start to address this question of quality and trust in citizen science data. And so, you know, I know there are people in the room here who work on this as well. It really is an area, there's lots of citizen science data. We can either dismiss it and say it has no value, or we can try to address it and we can try to figure out how to make it better. And I think that Bayesian statistics gives us a good framework for doing that. One of the second question that came up in this area that I'd like to talk about is this idea of model transfer. So with the project that we have with Virtual Reef Diver, this is now extended to other reefs in the Pacific area. And we don't know much about those reefs. We know a lot about the Great Barrier Reef, but not so much about these other ones. And so how do we transfer a model that developed in a rich source domain to a low data target domain? Now there's some different methods for this, so we think of this as transfer learning. So if we're looking at a neural network, for example, we'd peel off the top layer of a neural network, we'd fit that to the new data area, and then we would put it back onto the architecture for the existing model. And so that's one way that we could do very fast transfer learning in a computer science area. And we could learn something about that approach in our models if we thought about it as these hierarchical models where we peel off sort of the sampling layer and then to model that where we have enough information to a new setup. Where we don't have a lot of information though, we have to start thinking about other ways of doing it. And so one idea is to think of this as a model misspecification approach, and I'll just point to, I know Josh Bond's in the audience somewhere. There's Josh, yep, there he is, up the back there. So Josh is involved in this work with Adam Bretherton here, who's looking at ways that we might be able to do this. And Brodie Lawson is also thinking about this from an information geometry perspective. So I'd like to just talk a little bit about the work that Brodie's doing, and this is work that we've just sort of started to put into the context of this model transfer. So Brodie's question is, we want to know the distance, the statistical distance between two distributions. And so what we want to be able to do is to sort of map from one distribution to another. So just take it back to distributions for a moment rather than whole systems. And we want to think about the paths of shorter distance. If we knew about those, then it's going to help us with this sort of transfer question, but it's also going to help us with a lot of sampling problems that we have as well. And so we want to think about calculation of those optimal paths from one distribution to another. And it's interesting because that calculation of the optimal paths is often unwieldy, except for very special cases. Okay, so this is something that any of you may know about, I'm just learning about. But what we did was focus on just the multivariate normal case for a starter and understanding information geometry in this context. So very quickly then, this is the supported version of model transfer via information geometry. Going to think about a multivariate normal distribution parameterized by a mean and a covariance matrix, a vector of means and a covariance matrix. And I want to find the distance between 2 points. And I'm going to use information geometry to account, because it's not just a Euclidean distance between those 2 points. There's going to be curvature based on the covariance matrix effectively between the two distributions. And so I'm going to define a metric tensor, A, and a distance that's going to be traversed when the coordinates are infinitesimally increased. And if I can think about that like very, very small increase, and I can get rates for that, okay? I can get answers for that. And so here are some ideas about how I can go from one distribution to another. On the right, top right is what happens in a bivariate sense. On the bottom right is what happens in a trivariate sense when I'm moving across in the mu space here, okay? And I'm looking at just sequences or segments of the sigma space, of the covariance space. And so that's what this kind of picture is what I'm looking at here. And I'm trying to figure out what's the best path to get from one distribution to another. And when I'm in that very, very small space, that's okay, I can do that. But when I'm actually in larger distances, which is a sequencer, obviously, of those very small distances, then things start to get unwieldy, because I need to know then what's the minimum distance path between finitely separated points, or geodesics, accounting for this warping in space. And so the paths then will be found by solving these geodesic equations that you can see here. This is for the multivariate normal case. And if I have x and b, which is going to be d mu dt and d sigma to t at t equals 0, then if I knew the initial velocity, and it's going to be a constant velocity across these different paths, then I would be able to solve this. Okay, if I knew that initial velocities, initial x and b, then I'd actually have closed form expressions, and I'd be able to get from where I am now to where I want to be. But the thing is that there's no known solution for those initial conditions. And so what I want to do then is to think about shooting methods. So I'm going to sort of shoot in a direction and then adjust for it. So I'm going to shoot in the mu space and then adjust for it in the sigma space. And when I do this, please come and talk to me afterwards, or read the paper if you want some more info about this. But there's different ways of thinking about how we shoot and then how we correct for our shooting. So in order to be able to get from where I am now to where I want to get into this other distribution. So it's like, going into space. We need to be able to shoot out into space and then correct and see if we can land on the moon or something. So this is this idea, but in much more sort of multivariate normal space. When we look at doing that then, there's different methods that we can use for that shooting, and it turns out that the moment averaging approach actually works best in this particular case. Now I'm talking about this because these ideas were still brewing up for the whole big picture model transfer. But thinking about model transfer in the big picture, from transferring from one reef to another, motivates the thought about model transfer even from one distribution to another distribution. And so then that becomes a question of bringing together applied maths and statistics to think about how we might solve that problem, and then how we might solve the larger problem later. And I think that if we can come up with good methods for model transfer, this is really where being Bayesian in the 21st century really will play a role, because there are so many problems where we have models in one context we would like to extrapolate to another context. We're told we shouldn't do that, but we're going to. And so how do we do that in a principled manner? Right, challenge 1. Challenge 2 that I'd like to talk about is taking a completely different tack. And instead of talking about reefs, I'm going to talk about sport. So how many people in the room are involved in some sort of sport? Okay, all right. So you're into this one. So this is called Aussie Star. So this is Australian Sports Technology Analytics Research Hub. So sports is a big business. Sports analytics is also a big business. The $2.2 billion US dollars in sports analytics that you can see there on the middle left is actually going to be $29 billion by the year 2029. So lots of money in sports analytics. If you hadn't thought about a career change until now, it's a good time to think about it, okay? I never thought I'd be into sports analytics, but here I am, because we have all of these kinds of events. Now, we've got Paris 2024 coming up in a few weeks. You know, we've got the Wimbledon. We've got all sorts of different sporting events. We've also got esports as well, and we've also got recreational sports. So you'll see on the, let me see if I can do this. On this one here is actually the Murray Carnival. So this is an Indigenous sporting event that's held every year. We're going to put wearables on our juniors here and track them around the field and have a hackathon. So if anybody's not doing anything in a few weeks' time, want to come and join us, then we'd love to have you involved in analysing those data. But so there's a lot of sport here, and I'm pretty sure that there will be more than one person in the audience who's covertly looking at their phone, checking some sort of sports results right now. Just so you know. Right. So there are challenges and opportunities here. The challenges are we've got all sorts of data, right? This is a microcosm for all the problems that I've pretty much encountered anywhere else in sport, but the data are also siloed, okay? And so there's a lot of questions there, challenges also in how we access data, and privacy and ethics also. So in Australia, there's a lot of commentary on this. We're going to have the Olympic Games in Australia in 2032, and we need to get our act together is basically the message that we've had on sports analytics. So we've been asked to envisage a solution. And so we're developing a data science kiosk, which is sort of semi-automated. Somebody's walked through those doors. Semi-automated platform for finding out how to analyse data. That's one thing that we've been doing, and also this Aussie Star Hub. So, just as a call out, we have funding for 3 professorial chairs in sports analytics in Brisbane, if anybody's interested in moving to somewhere where it is warm. Then please let me know. So we'll be having these positions. Right, so there's a couple of challenges that I'd like to talk about. So we've gone from sport generally, which is everything, you know, all sorts of challenges. But what I'd like to do is to talk about 2 of them in particular. One of them is about finding the dimension in high-dimensional data. And the other one is finding clusters in complex systems. So just 2 out of many of the challenges. So the kind of data that we're looking at for this is cycling data, where we have an accelerometer on a cyclist or a wearable on a cyclist, and the curve here sort of shows the area or the path that they're taking, and also the acceleration along here. And this is showing it in sort of time, space here, what's happening. Over here we have a game that's being played. We have computer vision that's being annotated to look at the play for different players. And so the question is, you know, how do we find the dimension in these kinds of data? Back to Edgar again, Edgar and Paul Wu. Paul's done a lot of work in this as well. We've been thinking over the last few years about how to do Bayesian statistics in sport, and in particular, in collaboration with Antonio de Mira. Where's Anto? Up the back there, yeah. So this is Anto's hammer that she brought one time to Australia, looking at intrinsic dimension. And so I'll just talk briefly through this. So apologies to Anto for this. But the role of intrinsic dimension in high-resolution player tracking data. And so we think of data that's being sampled from a density, and it's going to be approximately constant in the region defined by the second neighbour in each point. And so we're going to think about, for a particular point, what's its first-order neighbour and its second-order neighbour, and we're going to take the distance from the point to its first-order neighbour and the distance from its point to its second-order neighbour, and take the ratio of those distances, and that will have a Pareto distribution. And the Pareto distribution, the parameter of that Pareto distribution can be considered as the intrinsic dimension of those data. So if we think about that, that's fine. When we don't have this constancy across the space, we can think about having it as a mixture of Paretos. And so we can then start to model this intrinsic dimension of the data. So we have the full dimension of the data, but what's the sort of the underlying intrinsic dimension is going to be sort of characterised by how close and far apart the points are in the space. And this is what we're doing here and fitting that as a mixture in a Bayesian context. And so for basketball then, we're looking at intrinsic dimension in basketball, and this particular game you can see here, but the kinds of questions that intrinsic dimension can sort of start to help us to understand is how is the placement of the players in attack and defence related to the success of a play? How do teams that have greater offensive ability produce successful shots from more unique locations in the court? Other sorts of questions like this that we might be able to think about answering. So we took some games from the NBA. This is data that is online. And we looked at a game from the Cleveland Cavaliers and the Golden State Warriors in 2015. And we measured this intrinsic dimension. This was in shooting for the baskets. And what happened with the intrinsic dimension, you can see as the players move into the play for the shot, as time goes on, what's happening with the intrinsic dimension. Okay, so you can see that pattern. What it shows is by calculating this that we do see a difference between the intrinsic dimension for teams that are playing away or playing at home, and also teams that have won or teams that have lost. So it's like the surprise in the data or the consolidation of the players. So this is sort of something that this intrinsic dimension measures, but we do see these differences. We also see a difference in the intrinsic dimension based on the winning margin of the games, and also what happens with intrinsic dimension over time. So this is the pattern here. And so we're learning about the game using these sorts of new forms of statistical measures of high-dimensional data. And so many of us are working on high-dimensional data, and we can apply it to these kinds of areas. So this is interesting for us to be able to look at complex movement patterns and being able to translate that into more coherent statistics and to be able to then guide teams in their play. So the second challenge in this second question is really about finding or being able to model complex systems. Now in sport there's a lot of complex systems. So I'm just going to point to one of them, which is recurrent injury. And for many of you who are sports people, you will know that this is really a big issue. Okay, you get an injury and then you get a recurrent issue. You're watching your favourite team and somebody's out for injury. Injury is a really big issue. And so there's a whole lot of factors that are involved in injury, and often you can't just write it down as a regression equation, and it's got a whole lot of biophysical issues as well as the environmental issues and the play issues and the personal issues and so on that need to come into thinking about it. So we're going to think about modelling recurrent injury as a Bayesian network. And we find these Bayesian networks really useful for these sort of more complex problems. And the sort of Bayesian network I'm going to be talking about, knowing that there's many of them, is just this sort of directed acyclic graph where we think about a response and we think about, so you're not meant to read the actual network here, it's just the architecture of it and what it looks like visually. But what we're going to do is think about a response. We're going to think about what are the factors that affect that response, what are the factors that affect those factors, and we build ourselves a graphical model of that. And then we quantify it. So we can quantify it with continuously, or we can quantify it with conditional probability tables. We often find that's useful to reflect the resolution of the data and also for calculation purposes. But we find that we can quantify different parts of these networks with different types of data. Now, we've used these kinds of networks to bring together different knowledge, to create conceptual maps of the drivers, to quantify the maps with all kinds of data, and to use it as a knowledge repository to identify key drivers. So once we've got this model that we've quantified probabilistically, we can flow those probabilities through and find the probability of the outcome. We can also ask what are the main drivers of an outcome given the other factors in the model. We can also ask, what if we change one of those factors or those inputs? How does it affect the outcome given everything else in the model? So they're very useful in this sort of complex decision-making and management processes. We've used them for biosecurity. We've used them a lot for conservation of cheetahs and jaguars and koalas and seagrass and so on. We've also used them for industry sustainability, so for the wine industry, which I think we all should work on. So we also use them for COVID. So a lot of work in looking at the implications of cost-benefit analysis of vaccination and lots of the features that go into that with all this sort of scrappy information that we have. So these were very helpful in putting together a model that's now been used by the Immunisation Coalition in Australia. And so we can figure out then what's the probability that you're going to die from COVID or die given that you're vaccinated or not vaccinated, and different kinds of morbidity and mortality outcomes. We can also use it for a business sense for these kinds of models when we extend it to a dynamic Bayesian network now, where we're going to have a system where we need to think of changes over time. And so this problem here was about dredging and the impact of dredging on seagrass. Seagrass is such an important feature of our underwater systems, and we wanted to know, well, if we can come up with different dredging regimes that would protect seagrass. And the picture down the bottom here is actually looking at the resilience or resistance of seagrass. So when there's actually a dredging event, then it decreases here, and then it has to grow again. And so depending on when the dredging actually happens, which is shown by these little circles here, these are different regimes of dredging here, and what will happen to the seagrass over the different months according to those different regimes. And so this was the question that we were asked, and we were able to address this using these sorts of dynamic Bayesian networks. When we did this, we were able to show that by careful modelling in the way that we did using these kinds of approaches, we were able to get a 4-fold reduction in seagrass recovery time and a 35% reduction in extinction risk. So we can make a difference with these kinds of models. This is work that's been really led by Paul Wu, my colleague, and one of the questions that we asked about this then was about compute time. And so this was the challenge that sort of came out of this kind of work, was we have these very complex systems now and complex models, and so we want to be able to do better compute time, and we also want to be able to cluster in some ways those nodes. So how can we come up with ways of understanding which nodes are best sort of layered or clustered in this kind of network approach? And so what we did then, and this was work that's being led by Paul, is to look at clustering nodes in Bayesian networks. So a Bayesian network is just this directed acyclic graph, and the goal of inference is to find the marginal probabilities for every node given observations or evidence in this directed acyclic graph. So in a dynamic Bayesian network setting, it's the same deal, except now we can sort of think of this as hidden Markov models and analogues of common filters and so on. So what we're going to do in the clustering then is we're going to assign to each node a value u, and then we're going to look at the cost that's associated with actually traversing the network. And by doing that, then we can start to look at which nodes should we cluster with which other nodes. So we're going to try to optimise the cost of this network. And so through this through a particular mapping here. And so this idea then is about looking at layering our network or clustering our network so that we reduce the cost of actually traversing that particular network. So you can see here the kinds that we're just thinking about probability tables, as I said. So this is conditional probability tables. A here, which is the node up the top. Where my little pointer's gone? Up here. So A here is going to be parameterised by just in two states, A and not A here. F given A, this one here, is only dependent on A, and so we're going to have this 2 by 2 probability table here. And so when I look at the probability of F then, I can multiply through all of the probabilities. So D here is going to be given by B and A, and so on. So I can see the whole sort of trajectory of the network being given here. And so then I can look at this probability statement here for the probability of F based on all the nodes in the network. So this is what I would get if I want exact inference, and this is of course why it takes so long. So what we're going to do then is to think about this dependent map clustering, or dependent cluster mapping here, and I'm going to think about layers and clusters and cluster layers. I'm going to just skip over a little bit of this, but just to let you know that when we go through the actual inference approach for this and look at the performance, then we can show that these sorts of clustering methods can be very useful in reducing both the computation time, but also increasing the inference in these kinds of Bayesian networks. So we can find optimal clusters with these kinds of approaches. And this can give us new research. It can be new research in inference about which nodes are related to which other nodes with respect to their distances. We can also look at memory-efficient computation trade-offs, and we can also look at embedding BN inference in an MCMC environment, which is pretty exciting for us as well. And there's other new research directions that you can see there as well. So thinking about this larger question of sport, and then this smaller question of injury in sport and how we model that, and thinking of that as a Bayesian network and thinking, well, we use Bayesian networks sort of like bread and butter in our context, in this context. But what are some of the questions that we need to, coming down again to, what are some of the questions that we need to resolve in order to be able to step back out again? So step back out so that we can use these sorts of networks and these kinds of challenges in this century. The third challenge. How am I going? 7 minutes? Perfect. Right. The third challenge here is about the Australian Cancer Atlas. And this is another platform and product that we have developed that I believe has really sort of tried to address the a need in Australia. And we've used a Bayesian spatial regression model to model cancer across Australia. And so regardless of what kind of spatial model you have, what we've done here was to use a Bisag-York-Mollier model for reasons of for the neighbourhood structure, mainly because of the kind of geography of Australia, that this just worked best for us. But what this atlas does then is it's a web-based platform that gives us estimates of incidence and risk based on that Bayesian model for each area of Australia. We've got about 2,000 small areas of Australia and about 20 different cancers. We've now developed this for a spatial temporal model as well, and so we've just released that version about a month ago. And so based on this then, and because we do have this underlying Bayesian spatial and spatiotemporal model, we can start to look at what's the probability of one area being different to another, what's the probability of different cancers being related, what's the difference between being over a particular threshold and so on. So all of the kinds of Bayesian inferential architecture that we know, we can apply now to this setting. And when we do this, then we can also start to see what are the spatial inequalities in cancer across Australia. And so one of the really big things is that there is a difference in equality of incidence and survival from people who live in the country and people who live in the city. So especially in survival. And so the question is, well, we shouldn't have that in Australia. You know, why should people who live in the bush have worse survival than people who live in the city? And we can even quantify that. We know how to do that through our Bayesian models by looking at like how many people then could we save if we didn't have that kind of inequality in Australia. And so that's then led to a lot of media interest, and which has also then led to changes in policy in terms of people who live in the country getting a rebate to at least get some treatment, attend treatment in the city. So these Bayesian models, we set up to be able to develop this kind of platform and have really led to some policy changes. So again, there are some challenges and some opportunities through this work. And so by building the platform, if you like, then we've also got some of these questions that we needed to address as well. One of them is about extending the model. So we want to understand the why. Now, why do we get these kinds of changes? And so much like the virtual reef diver, we're going to start allowing people to geotag their treatment stories to the atlas. And then we're going to try to extract information from those treatment stories and include it with our data that we have on cancer. Not quite sure how to do that yet, but I do a lot of arm waving and saying, we can geotag these stories and analyse them and so on. So if people who know about doing that, love to hear about it. We can also add covariates, and we can also think about combining different kinds of environmental and biophysical models. And so I'm just going to touch on that quickly through sloppy modelling. And this idea of sloppy modelling has been led by Gloria, as you can see here, and a number of other people. The idea is that we have complex systems, we have a lot of data, but it's really low compared to the number of model parameters. And so we think about which parameters are really driving a system, and how can we learn about that. So what we're going to do then is to think about not just the model parameters individually, but also parameters collectively. And what's the combinations of parameters that are more important in these kinds of systems? So we think about then stiff and sloppy parameters, and there'll be people in the audience I know who work in this area, but there's stiff parameters, then the ones that really significantly influence the model predictions. They're like your control knobs. And they're really tightly constrained by the data. And then there's the sloppy parameters of the others that really don't really respond to the data. And so we can think about then model sloppiness as being the sensitivity of model data fit to changes in sets of parameter values. And so we can characterise the topography of a surface then, describing how the model data fit depends on the model parameters in the vicinity of the best fit parameter values. So the Bayesian approach for this then is going to be to look at estimating the posterior distribution by fitting the model to the data, and calculating the sensitivity matrix really based on the Hessian, Bayesian Hessian of the inverse posterior covariance matrix, because that's really going to control what's happening in this model. And then we identify the eigenparameters that are more or less sensitive to the model data fit through this eigendecomposition of the sensitivity matrix. So just showing you an example of this. This is a very simple ecosystem network. So it's just got 4 equations, but it's got 8 constitutive equations and 20 different parameter point estimates here. So it's a poor data system. This is what's happening with the equations. So there's just 4 of them, but it's quite complicated and lots of different parameters. So what's actually happening here? So we fit the results, fit the model to the data here, and we've got this time series data, very poor time series data. And based on the parameter marginals, what we find is that there's only really a few parameters in that whole system that's actually controlling the whole setup. And so these have a strong influence on the quality of the model data fit. So this idea of stiff and sloppy parameters and the characterisation of that through these eigenparameters really can help us to understand which of these combinations of parameters are really driving a system. And so I see a lot of potential in bringing this kind of work into our statistical modelling as well. And so we can look at modelling measuring certain parameters, and if we get those right, then, and we can get more data on those particular parameters that are driving a system, then they're the ones to focus on in future sampling. The rest of the parameters are just going to be sort of sloppy in the system. I just wanted to touch briefly on other work on the role of priors, and to give a shout out to work that's been done by my group and a whole lot of other people in the literature, of course, around subjective priors, around thinking about how we can automate priors. For example, shout out to Judith Rousseau. Is Judith here? So yeah, thanks Judith. Who I've learned a lot from and taught me about the number of components in a mixture model and how we can set the prior to be able to make sure that even if we're overfitting a mixture model, then we can obtain the correct number of components, which has been really, really helpful, and we're extending that to hidden Markov models as well. Looking at plausible priors as well, and so thinking about setting plausible priors in a way of, if we think about what would our future data look like, and what statistics on the basis of our future data do we care about, and then what values of those statistics would we find plausible or implausible. And if we can do that, then we can go to our prior predictive distribution before we've seen any data, and we can ask under particular types of priors, then are we going to be in the plausible or the implausible state if we actually saw our future data. And so this can give us a way of being able to parameterize or to constrain our parameters. Okay. Can I borrow 2 minutes? How long are we up? Are we out of time? Okay, all right. So the last thing I want to talk about is data access. And so this is really important for our Cancer Atlas here, where we have different data in different silos, and this is also the case for our sport data too. And we have data held by different custodians that can't be shared easily. And so an area that I see of great potential, and we can address this as Bayesians, is in the area of federated learning. And I think this is really going to be a game changer in the way that we do large data analysis, where we have data in different, held by different data custodians, and instead of trying to access those data and aggregate it, we learn about doing our analysis in the cloud, if you like. And this is going to be important for us to think about how we actually tailor our Bayesian models to be able to address these kinds of this kind of federated learning approach. And so if you think about the federated learning schema, then we have data in different nodes, and we're going to do the analysis in the cloud. And a really nice early example of this work is by the Dutch Cancer Agency, that combined data from different countries to learn more about cancer, and developed an open source federated learning platform called Vantage 6. So this was my first exposure to this federated learning in practice. And so what happens then, if we have a general linear model, then we don't actually see the data. Everybody keeps the data, each data custodian keeps their own data. We share summaries of those data, summaries that are important for our analysis. And so if we do the original data, we have the data in its own silos. We then collect those data, aggregate it, and then do the analysis. If we do the federated approach, the data stay with the different data custodians, and then we do the analysis in the cloud. So Connor Hassan, a PhD student, along with Josh, again, has been working with federated learning for different kinds of systems. So both in the hierarchical system, so where we have information or parameters we want to learn about for the particular nodes, and then also parameters that we want to learn about globally, also for spatial information and also for vertical analysis as well. So I'll just skip through some of this to show you then for the vertical work. This is very new, so this vertically partitioned data also being done when Connor was being hosted by Antonio de Mira. And so the idea here is this is some of the harder work, because each data custodian owns a different variable, so to speak. And so when we think about this, then we need to figure out how we can do this in an efficient manner. And the idea here is to use this sort of augmented scheme and an amortised variational approximation to manage the computational cost. So this is new work, and it's very exciting for us to be able to think about how we might actually be able to implement this. So just close your eyes for a minute. I'm going to go through challenge 4. I'm not going to show this, but I'm going to just go then to a summary that says, we've talked a little bit about sort of some of these challenges that I've been involved in, have really tried to address these bigger projects, but how they've elicited and motivated different individual discussions. So we've come a long way from when Turing said, what we want is a machine that can learn from experience. I think, we're starting to get there, but we've still got a really long way to go. And there's a lot of work that I think we can contribute to in this century in, for example, AI, in quantum, in science and society. We can do that through Bayes. We can do that through our methods that we can publish in papers like Bayesian analysis, and a shout out to our journal. But also I think we can do it so that we really can start to address some of the really big issues in our society. And together, we can really change the world in 2020 and the 2020s. Thank you.
Thank you very much, Kerrie. I think we have time for questions, since we have a break after. Any question to start? Yes, Judith?
Thanks, Kerrie. It's very impressive. Just out of curiosity, these platforms that you develop, how often do you have to retrain them? Do you ever retrain them? Or
In terms of the data?
Yeah, or the parameters of the model behind?
So the actual analysis is happening at sort of regular intervals behind the scenes. Well, sorry, for the virtual reef diver. Sorry, hang on. For the virtual reef diver platform, that's happening at regular intervals behind, where we're ingesting the information and updating the analyses. For the Cancer Atlas, then that's just being done at a much slower pace, because we only get the data intermittently at the moment. When we get the federated approach set up, then we'll be able to do it in more realistic time.
Important, or is it like an issue in your case? Or?
Learning when to retrain?
Yeah.
Oh, I think that's a really interesting question, and some of it depends on the velocity of the data, of course, it's coming in, and also the needs, the needs of the users to, how often they're making decisions as well. So there's really no point in updating a system, faster than like doing many updates before somebody needs to make a decision on it. But interesting.
Very, very interesting and impressive, and also love this last slide. But just a comment, so you are describing big projects, no? So an idea of how many people are involved and how different expertise, so I can imagine a statistician or other expertise to actually physically build the platforms also. So the size of the group of people you work on.
Yeah, thanks, Sonia. So, so the interdisciplinary teams is just really, really important. So for our Cancer Atlas team, there's probably about 20 researchers, but working on different parts of it. So epidemiologists, people who are very involved with cancer, some modelers, some software developers, and similarly with virtual reef divers, same sort of thing, but just a different skin for the questions. But certainly it's a combination between expertise, domain expertise. It's really useful to have people from computer science, maths and stats in the room as well, so we just get that different perspective, and then also our software developers as well.
Just kind of struck me on a few of those examples where you're obtaining data in some sense kind of, I won't say passively, but people are providing you the data. And the issues of like selection bias or ascertainment bias come in. There's this kind of traditional tension between non-Bayesian methods and think very carefully about ascertainment and targeting marginal effects, and Bayesians which just condition on the data and then build joint predictive models. Does ascertainment bias come in? I'm thinking of the kind of your first example of people providing photos of the reef where it's nice to dive or not nice to dive. Thank you.
Yeah, sure. So you're right. That does come into it a lot. So I just touched on some of the questions here, or some of the challenges, but of course there's others that we really need to address as well, and that's one of them. It's like so many of these things, we're going to find the coral where people go, and people go where the coral are in that particular example. We can get around that in some ways by looking at other data sources as well to try to calibrate what we're seeing, which is what we try to do, and also try to fill gaps. But I mean, in some ways we're not. We're fortunate in the virtual reef diver example that we have long-term monitoring sites at specific locations, so we do get some sort of understanding of that. But otherwise, we'd really have nothing in between. So you have to figure out if this something is better than nothing. Sometimes it's not, but in this case, it seems to be.
Hi, great talk. Two more challenges that you haven't discussed. First of all, most of us, we think that scalability is a big issue and challenge for today's problems in Bayesian inference. And the second is multiple sources of data. And I think in both of these situations, we have a long way and very interesting approach. For example, in scalability, maybe sequential updating will give a solution. So I would like a comment on these two challenges.
Yeah, thank you. So the scalability question is really fundamental to us as well, and so we borrow from a lot of the good work that's done by others. In a lot of the work we try to do, and I think what's interesting is that we think about these I was going to say the usual kind of approaches like data sharding and so on. So, consensus Monte Carlo. They weren't so usual a little while ago. So what we're hoping is that there'll be better methods that become usual soon as well. But what's also really interesting is we're not there yet, but I think quantum's really going to change a lot of the way that we do things, and the people that we have in our Bayesian community who really start to understand that and start to figure out good ways that we can capitalise on that. That's going to be a game changer for us, pretty much as much of a game changer as MCMC was in the beginning.
Thanks for the lectures. The question, so you discussed a lot of the open issues, but more from the probability theory side, where I also come from. Where do you see the future of Bayesian approaches in connections to probability theory, which develops, I would say, jointly with machine learning, with Bayesian and other approaches, and is connected?
Yeah, I would be interested in your take on that more than mine. But I mean, the probabilistic machine learning probability, I think probability theory is just fundamental to what we actually do in Bayesian statistics anyway, and certainly in our algorithms as well. So, I think there's some really interesting advances in probability theory that we would like to see brought across and into our methodology here. And from the early days, having a sort of reasonable understanding of that probability theory was really important. I think now we sort of get more to the computational and maybe a less deep understanding of that. So I think we need the whole community and different segments of the community to have expertise in different parts, but for us to listen across those different parts as well. So not everybody is going to be highly skilled in probability theory, but we certainly need to know about it and to respect that there's good developments that can come across and improve what we do. So.
Okay, thanks.
So,